Morning, everyone. Today we would like to study modeling in the time domain. This is chapter 3 in this book. So in this chapter, in fact, we need to cover mathematical modeling, which is called state space representation. And state space representation, we will use it for linear time invariant systems. We will try to model systems which we did already in chapter 2, such as modeling of electrical and mechanical systems. But in this time, we need to put it in a state space. And in the last 3 minutes, we try to find a transfer function, but here we try to find the state space representation of your system. We need also to learn how to convert a transfer function into state space. This is very important. So if your system is given in a state space representation in frequency domain, it would be nice also to transfer it into state space representation so we can work with our system in the time domain. We need also to convert the state space representation into transfer function. So now we need to do the opposite. If you have your system in time domain, and if it is represented as a state space, can we convert state space representation into transfer function? And also the last section in chapter 2, it was about linearization. We need also here to cover how to linearize that space representation of a system. So in chapter 2, it was modeling in frequency domain, just to revise quickly what has been done in chapter 2. So we studied Laplace transform of a time function. Also, we studied how to find inverse Laplace transform, how to get a transfer function from a differential equation, and how to solve a differential equation using a transfer Laplace transform, in fact, of transfer function. So it was easy to find the transfer function, which is g of s equal, for example, y of s divided by r of s. And substituting the value of the input, we can find the output in S domain. And after that, we can use partial fraction expansion and we'll try to find your function in time domain, or the solution of your differential equation in the time domain. Also, we studied transfer function for linear time invariant system. We have been working with some examples, such as electrical network, mechanical systems, rotational mechanical systems, gear systems, electromechanical systems, and also how to produce electrical and mechanical circuits, how to linearize a linear system in order to find its transfer function. So this one, you can take it as a quiz. It's RLC circuit, and we did that last time also. And we need here to find the transfer function, which is VL divided by VS. So we need to find the transfer function, which is VL divided by the input. So we can say that transfer function here, it will be VL of S divided by V of S. And last time we found easy way for doing this by using by converting this one into replacing all those components with the impedance, right? So here we have L equal 1 in fact, right? So the equivalence of this one, it will be LS. So it will be just S. And of course, R, it will stay R as it is because it is constant, and you need to have the current like this one, I of t. So in this case, you can just write the summation of the voltage across or around the loop, and you can try to solve it. Remember also we used this table last time. When you look into this table here, it's table 2.3. So we used this table from voltage current, voltage charge, and impedance relationships for capacitors, resistors, and inductors. And it's from chapter 2, in fact. And the most important here is to replace its element by its impedance. So if you have a capacitor, just replace it with 1 divided by CS. If you have a resistor, replace it with R. If you have inductor, replace it with S. And write the equation. So the equation will be Z. It will be like Z multiplied by I equal V, for example. Z, this is the impedance, total impedance. So if you want to find the solution of this example, you can find it in chapter 2. It is example 2.28. It is in page 92. So now we need to go back again to chapter 3, which is modeling in the time domain. In fact, there are 2 approaches for the analysis and the design of feedback control systems in general. One we studied in chapter 2, and one we will study it here in chapter 3. The one which we studied in chapter 2, it was classical approach or frequency domain approach. So the classical approach or frequency domain approach, where we try to convert the system differential equation into transfer function. We did that, in fact, in chapter 2. So in chapter 2, we can say that this is the classical approach, where we are working with the system in the frequency domain. And to do this, you need to get transfer function. And to get the transfer function, you need to convert your system's differential equation into transfer function using Laplace transform. And therefore, we studied Laplace transform. And the second approach, it's modern. We call it modern approach or time domain approach. So the modern approach, in fact, it's time domain approach. And in this case, we need to represent the system in a state space. So we need to have state space representation of your system. And we can use this state space representation for modeling, analyzing, and designing wide range of systems. Transfer function, in fact, we can write it like G of S equal Y of S divided by the input, which is U of S, or for example, R of S. So this is an S domain, but it's this base representation. It is a set of two first order differential equation. So the first one is X dot equal A multiplied by X plus PU. And this one we call it state equation. This one we call it state equation, and therefore we call this one state space representation. So this equation we call it state equation, and we have another equation which is called output equation, y equal cx plus d. So this one we can call it output equation. So at the end we have you can have also inputs, or so maybe we can call this one it's y of s divided by input, which is u of s, for example. I mean, if your system is like this one, so this is g of s. We have here output, which is y of s, and we have here the input. It could be reference or control signal, for example, so it could be u of s. So the same here, x dot equal ax plus pu, y equal cx plus du. In fact, this one has it has a flowchart or a block diagram representing it, but it's the same. This one, it's in time domain. This one, it's in time domain. And this is a modern approach for controller design, but this one, it's in frequency domain. So this is the classical approach. So we spend chapter 2 in frequency domain, and in chapter 3, we try to talk about modeling in the time domain. But you just need to know that converting a system from time to frequency or from frequency to time, it's easy using Laplace transform or inverse Laplace transform. So what is the difference between if we try to compare between transfer function representation and state space representation? State space representation, we can say that it's SS, state space representation. So transfer function, you are working in S domain. Here we are working in frequency domain. When your system is represented as a transfer function, you need to know that we are working in the frequency domain, but state space representation, we are working in time domain. Transfer function, when we are in frequency domain, this is the classical approach. This is the classical approach. While when you are working with state space representation, this one is a modern approach. In transfer function, it's based on converting your system's differential equation into transfer function. So if you have a differential equation representing your system, you need to convert it into transfer function in order to be able to check stability, for example, and design a controller in the frequency domain. In state space representation, we have also a differential equation. This differential equation, it could be higher order, it could be second order or third order, for example. So we need to convert this differential equation into a set of first order differential equations, right? And this set of first order differential equations, in fact, this is the state space representation, because state space representation, it's x dot equal a multiplied by x plus pu. So in fact, this equation is first order because we have here the x by dt. So it's a first order differential equation. So if you have a system, differential equation which is higher order, it would be second order or third order. We need to convert it into a set of first order differential equation. How many differential equations or how many first order differential equation? It will equal to your order, your original order. So if your system is second order, in this case, we need to get two equations like this one. So we will have x1 dot equal something multiplied by x1 plus pu x2 dot. So we need to have two states or two equations, two first order equations. If your system is a third order, we need to convert it into three first order equations. And after that, we will put those equations in matrix notation to simplify solutions. In frequency domain, we can rapidly provide stability and transient information, and therefore can help us to immediately see the effects of varying system parameters until an acceptable design is met. This is very quickly, in fact. When you accept approach in transfer function, it's very rapid. Even if you want to check stability by looking into your tools, it will be easy to discover quickly if your system is stable or unstable. But working with a status-based representation, it provides access to system state and the dynamics, which can help in identifying faults. It gives us more abilities, in fact, for making more complex stuff. We can design really more complex systems, and also maybe we can design systems which can detect faults in your system because we have states and we can identify states. So it's like patient in surgery room, for example, and you can see many things, right? When it is in time domain or when it is in status-based representation. So at least we can identify faults. Transfer function, it has limited capability or applicability. It can handle only linear and time invariant system. We need to, if you want to get the transfer function, you must linearize your system. It can handle only linear and time invariant system or single input, single output system. So your system must be single input, single output. Because when you draw the block diagram, in fact, here, you have single input, you have single output. The input is U of t, the output is Y of t. If your system has two outputs, in this case, you need to get one transfer function for each output. It could be more, in fact, because if you have two inputs, maybe this transfer function, you need to get four transfer function. So it deals with single input, single output, and also systems. We assume also all our systems have zero initial conditions because in the definition of the transfer function, it is the Laplace transform of output divided by input at zero initial conditions. So we need to assume that we have zero initial conditions. But in case of status-based representation, it can handle all systems. It can handle linear systems, time invariant systems, nonlinear systems that have some saturations and different types of saturations or different types of nonlinearities, such as saturation, dead zone. It can deal also with systems with non-zero initial conditions, right? Time varying systems. It's such as missiles, for example, with varying fuel levels. If you have a missile, so with time, in fact, it's moving, and maybe the fuel level will decrease over time, right? So you have different initial conditions, different operating points. So it would be much better to deal with it in a status-based representation, not using a transfer function. It can deal also with multi-input, multi-output systems. So if your system is complex and it has multi-input, multi-output, and couple the system, it will be easy to do this in time domain. Transfer function has limited design parameters, focusing only on the input-output characteristics, such as gain margin and in decibel and phase margin in degrees. So it has limited design parameters. We have only this gain margin and phase margin. So if you want to design something, your system to behave in some way in the time domain, it will be impossible because it's difficult to get those design parameters in frequency domain. But we have to deal here with gain margin and phase margin. But in case of time domain, design parameters, it could include, for example, maximum or peak overshoot, right? We need to have maximum overshoot of between 10%, 15%. Rise time, we can control the rise time, how much rise time we need to have. Settling time, correct? Delay time. Also, maybe also the max time, in fact. Peak overshoot and the settling time are used to characterize the disturbance rejection, while other parameters such as rise time are used to characterize the speed of the transient behavior. So in fact, when you are working with time domain, you will have capability to control your system in a much better way because you have more design parameters. transfer function is convenient for manipulating and analyzing complex feedback systems. And in case of state space representation, it's convenient for simulating complex systems. It's very easy to simulate. And I will give you an example, because in fact, our system in time domain, it's a first order differential equation. So it's x dot equal ex plus pu. And this is our equation y equals cx plus du. So if you want to simulate it, it will be easy. In fact, in time domain, you just need to define a for loop and you need to calculate x dot. So I will just calculate x dot equal ex plus pu. And if you want to get x, in fact, x will be x plus x dot, correct? That is it. So it's a kind of integration. In the system here, we try to integrate. And once you calculate x, you need to calculate y. So substitute this value into this equation to calculate y. So if you want to simulate your system, and I will give you an example in Python at the end of this chapter, where you can try to simulate your systems in the time domain. So it's convenient for simulating a complex system, and it can be used as a design tool where responses for changes in system parameters can be easily obtained. In fact, your system it's in the time domain, so it will be easy to identify system dynamics, faults, and so on, and try to modify your control system while it is running. So you don't need to assume zero initial conditions each time, because the problem here in frequency domain, when we're designing the system, we have the transfer function, which assumes that we have zero initial conditions. But during the run, if you have a missile, for example, and you need to change the controller parameters, it will be impossible to do this. If your system was represented in frequency domain, I must have my system represented in frequency domain so we can get access to real-time model parameters, for example. So in this case, we can make some changes and modifications while my system is in operation. We will go back to those examples before. I mean, it's a very, very simple example. It's RL circuits, and we need to write the differential equation of this one. And we need to find maybe transfer function first. And after that, we can try to find the state space representation. As I told you in chapter 2 that if you want to solve this problem to find the transfer function, we can just try to write it in S domain. So R will stay R, and L we replace it with LS, correct? Close the loop. This one will be V of S. This is my current, which is I of S, correct? So I can write the equation around this one using voltage, Kirchhoff voltage law. So V of S will be R plus LS multiplied by I of S, right? So if you want to get the transfer function of, it would be, I don't know, what is the transfer function which we need to get here. So if it is I of S divided by V of S, for example, it could be the current through R, for example. So in this case, my transfer function will be I of S divided by V of S. It will be 1 divided by LS, just order it, plus R. Divide both by L, so it will be 1 divided by L divided by S plus R divided by L, correct? So, so it's easy to do it. So this is the transfer function. If we need to write the differential equation of the RL network system shown in figure and convert it into transfer function. First here in this example, we need to find differential equation, in fact, which is describing it. When we try to get the differential equation, we try to go into elements which can store energy. So look into, so now we are done with this transfer function, but now we need to write the differential equation. When you want to write the differential equation, look into your system and look into the elements or components which can store energy. I have here R, L, and L. R cannot store energy, but L, in fact, it can store energy, right? So we look into the voltage across L. So it's VL equal L di by dt. So the voltage drop across L, it will be VL of T equal L di of T by dt, in fact, right? So differential equation, we just need to get differential equation, something which is d by dt, right? So in fact, we have here di by dt in this equation. So we can take it on one side. So divide both sides by L. So we can say that, okay, we have here di by dt equal 1 divided by L multiplied by VL, correct? In fact, we can say that I it's a state, correct? So now we have on the other side VL, but we need to represent V we need to represent VL in terms of other things. In fact, VL equal you can see that V of t equal R plus VL, right? And the voltage drop here equal VR plus VL. So you can say that VL is V minus VR. So this one will be 1 divided by L multiplied by VL. It will be V minus VR. What is VR? In fact, it's R multiplied by I. Correct? Okay, so now we are done. Just order it. So it would be minus R divided by L multiplied by I plus 1 divided by L multiplied by V, which is the input. So in fact, this equation, when you look into this equation, it's di by dt equal minus R divided by L multiplied by I plus 1 divided by L multiplied by V. So in fact, this equation, it's like this equation. Compare this equation with this x dot equal AX plus PU, right? So U is an input to my system, which is a source, V of t. So we can say that, okay, this V equal 1 divided by L, and I have here x dot, which is I dot, equal minus R divided by L multiplied by X. So you can say that A, in this case, it will be minus R divided by L. So in fact, this is first order differential equation. And we can say that, okay, this first order differential equation represents my system. So we can represent my system by this equation di by dt equal minus R divided by L multiplied by I plus 1 divided by L multiplied by V. So, but there are steps which we need to follow. So if you want to follow some solution steps, first we need to select the current I of t, for which we will write and solve the differential equation using the Laplace transform. We need to write an equation for I of t, right? We need to write this loop equation, L di by dt plus Ri equal Vt. We will look into the voltage drop here. Voltage drop here, it's VL equal L di by dt. So using Kirchhoff voltage law, so the summation of voltage V of t equal IR plus VL. So you can say that, okay, V of t equal VR, voltage drop across R plus VL. VR is I multiplied by R, correct? Plus VL, which is L di by dt. And this is V of t. So this is my differential equation. Just order it, right? So it will be L di by dt plus R multiplied by I equal Vt, right? So this is my differential equation. So this is a differential equation which we want to get. After that, if you want to get the transfer function from this equation, remember the definition of the Laplace transform of the transfer function, we assume zero initial condition. So just apply Laplace transform to this equation. So it will be V of s equal R plus Ls whole will be multiplied by I of s, correct? Because we are assuming zero initial condition, because we need to get, of course, we have here some zero initial condition. So Laplace transform of that part, if you don't have zero initial condition, this one, it will be L S, it will be L multiplied by S I of S minus I at zero initial condition, but we are assuming this one. So we will just set this one equal 0 just to make things easy. Because we assume that we have zero initial condition. So now I need to get the transfer function. So the transfer function will be I of s divided by V of s. So I can say that, okay, G of s equal I of s divided by V of s. So it will be 1 divided by Ls plus R. If you want to make it more beautiful, divide by this L. So it will be 1 divided by L divided by S plus R divided by L. And you can just draw this block diagram to represent your system. So the output will be I of s, and the input will be V of s. And this is what we got, in fact, right? So if we can go back here, we got the same transfer function here, g of s equal that part. So if you want to solve this one, if you want to solve, we got the transfer function as you can see here, g of s equal this one. And if we need to solve the differential equation, so we need to get a value for I of t, right? So yes, if we need to solve this one, so just assume, so just cross multiply, right? For this equation, do some cross multiply. So we can say that I of s equal that part multiplied by v of s. So I can say that, okay, cross multiply, so we will have I of s equal 1 divided by L divided by s plus R divided by L multiplied by v of s. So we need to see how much v of s. If v of s is a constant value, right? So maybe for some value of v of s. Yeah, okay, we will see. So the function I of t, I of t is a subset of all possible network variables that we are able to find from equation. If we know the initial conditions in the input v of t, we need to find value for v of t. So I of t is a state variable, and the differential equation 3.1 is a state equation. This equation we can call it a state equation, for example. We can now solve for all other network variables algebraically in terms of I of t and the applied voltage if you want to get other things. But first, I need to show you how can we get this one, this solution. Just forget about this one because we assuming that we have zero initial condition. So we have the transfer function, which is g of s equal I of s divided by v of s, which is equal 1 divided by L divided by S plus R divided by L, right? So what is V of S? First, we need to see what is V of S. So assume that V of S is 1 volt, for example, right? So in this case, I of S, it will be, so if V of T equal 1 volt, so V of S will be 1 divided by S. So cross multiply, so I of S will be 1 divided by N divided by S multiplied by S plus R divided by N. You know, to solve this one, we need to use partial fraction expansion. So it will be something like this one. We have here S, we have here K1, we have here S plus R divided by L plus K2. We need to find the value of K1 and K2. So for K1, multiplied by S and the set S equals 0. So it will be 1 divided by L divided by R divided by L. So it will be just 1 divided by R, right? It will be 1 divided by RS. The second part, S plus R divided by L. What is K value here? Multiply and substitute S equal minus R divided by L. So it will be 1 divided by L divided by minus R divided by L. So it will be 1 minus divided by R. So now we need to, so we can say that just take 1 divided by R as a common factor. So it will be 1 divided by R multiplied by 1 divided by S minus 1 divided by S plus R divided by L. Apply inverse Laplace transform. So in this case, I of t will be 1 divided by R, because this is constant, multiplied by what is the inverse Laplace transform of 1 over S? It will be 1 minus 1 divided by S plus R divided by L. It will be exponential minus R divided by L multiplied by T. So now we have the solution in time domain, correct? Now we have I of t. So we did that in chapter 2, in fact, and now we are repeating it, right? We are just repeating it. You have RL network, and you try to find a differential equation which representing your current and volt, and we found it, this differential equation. And once we have this differential equation, we can, from this one, we can get transfer function. So by applying Laplace transform to this one, we are able to get transfer function. And once you have the transfer function, you can do cross multiply. and after cross multiply, you will use partial fraction expansion and solve it. So now we have an expression for I of t. And as you can see here, I of t, it consists of constant part, which is the force component, and the exponential part. So in fact, in our network here, if it's first order system, in fact, so if you said that, okay, for V of t equal 1, how the output will look like, right? So the output will be, the current will go like this one. We will not have here overshoot or undershoot. It will be like this. Of course, we will have some, in fact, we will have some steady state error. So we should get here some ESS. ESS here will not equal to 0, right? Yes. So now we need to see how to get state space representation. If you have a differential equation, how can we get the state space representation? So there are some steps which we need to follow. And step number 1, we need to label all branch currents in the network. If it is multiple branches, or we need to label all branch current in the network. And in step number 2, we need to select the state variables by writing the derivative equation for all energy storage elements. So if you have any energy storage element, you need to write the differential equation which describes maybe the voltage across it. So if you have, so first we will start here. My network, it's only one loop. So we will label the current in it. So the current will go from the source, and it will just go from through R to L back again to the source. So we have only one loop. So we will label the current in this one as I of t. If we have two loops, we can say we have I1 of t, I2 of t, for example. And after that, we try to find state variables. How can we get state variables? We need to write the derivative equation of any energy storage element. In this circuit, in fact, we have R and L. R cannot store energy, but L can store energy. So we need to write the differential equation of the voltage across L. So the differential equation of this one, it will be VL equal L di by dt. So it will be this one. VL equal L di by dt. We will get this one from the table. After that, we will apply Kirchhoff voltage law and current law to obtain a differential equation describing your system, right? So we can say that, okay, by applying the Kirchhoff voltage law, we can say that the source, which is V of t, I will write it here. So we can say that, okay, V of t, which is a source, equal voltage drop across R, which is VR, right, plus VL, correct? So the voltage drop across the source will be VR plus VL. Okay, now we need to write it in a different way. What is VR? In fact, VR is I times R. We can just say it's R times R. What about VL? Yeah, VL, it's L di by dt. It's L di by dt. Correct? So now we have a differential equation. Just to try to get the I by dt in one side, right? We get this part in one side. So in this case, we can just say that, okay, so L di by dt equal, I will do it in more steps. So it will be L di by dt. Just arrange, order it, and take this one to the other side. So it will be minus R multiplied by I plus V. I will just put it V. Divide both sides by L. So in this case, di by dt equal minus R divided by L multiplied by I plus 1 divided by L multiplied by V, which is the input, right? So this is the equation which we got. So we will get this one. You see, we got this one. So this one is first order. I mean, the definition of a state space representation, it's a set of first order differential equation. This equation is first order, right? So in fact, we can use this one to represent my model in a state space representation. And because the state space representation, as I told you, it's x dot equal ax plus pu. So now we have the state equation, which will be di by dt equal minus R divided by L multiplied by I plus 1 divided by L multiplied by V. So I can say that, okay, my states x equal I. So my states will be x equal I, right? X dot equal I dot I dash, for example. A, B, A matrix, it will be, A matrix here, for example, it will be minus R divided by L. B, it will be 1 divided by L, right? U, which is the input here, U equal V, because this is my input. So in this case, I can just use this equation, and I will call this equation as my state equation. This one will be my state equation. This is my state equation. Now we need to write an output equation. So in fact, the output equation, it's based on the output which you want to measure. Maybe someone want to measure the voltage across R. So in this case, the output equation will be VR. And what is VR? In fact, it's R multiplied by I. So it will be like this. So I can have multiple output equations. But if you want your output to be, it could be just I. So in this case, Y will be just I. Because I'm interested to measure the current in this loop. Maybe a third person, he said, no, I want to measure the voltage across L. So in this case, Y will be VL. What is VL? In fact, VL, it's V minus VR. So VL, it will be V minus VR. What is VR? It's minus I minus R multiplied by I plus V. So it will be like this one. So in this case, I will focus only on the last equation. So in this case, in fact, the output equation will be Y equal minus R multiplied by I plus V. And the output equation, according to this state space representation, the output equation Y should be Cx multiplied by du, right? So in this case, C vector, it will be minus R, and the D, it will be D equal 1, right? So it will be like this one. So the most important in state space representation is the state equation, and the output equation is something which you need to select, right? Because you have a motor, for example, and the one would like to control the speed. So the output equation for him, it will be speed, because I need to measure speed. For someone else, you want to measure position. So I will measure position. If you want to control your robot, for example, maybe in this case, I need to control the speed and the position. So in this case, we will try to write an output equation, which will consist of my two states, which are the speed and the position at the same time. Because at the same time, I need to control both of them. Because I can control the speed and forget about the position. So my robot will move at a fixed speed, but it will not reach my destination, and the opposite. If you are interested to control the position and you forget about the speed, so I want to go from A to B, maybe the robot will go too fast or too slow. It will reach your destination because you are controlling the position of your robot. So it will be able to go point to point A, for example, or from A to B. But maybe it will be too slow or too fast. So in this case, maybe someone will try to control both of the speed and the position at the same time, and we need to do this in reality, right? So the point here is that state equation, it will represent the system dynamics. It's very similar to the transfer function, if you can remember it, because the transfer function, it is a transition from zero initial condition to steady state. But in case of a state space representation, we have two equations. One called the state equation, and this state equation, it will represent your states or dynamics. And the output equation, it's something which we need to decide, right? Something we need to decide. So the idea here is to, or the beauty here, in fact, is to, once you have the state equation, right? Once you have this equation, you can decide your output equation. I can have one controller for controlling the speed, and at the same time, also I can have another controller to control the position. And as you can see from the comparison between state space representation and transfer function, we can deal with multi-input, multi-output. So I can have a transfer function where we have multi-outputs, right? Multi-outputs means at the same time I need to measure both the speed and the position. But if you want to do this, in fact, in transfer function, it's impossible, because transfer function, it is used only for single input, single output systems. You cannot control two variables at the same time. But in case of a state space representation, it should be possible to control two variables at the same time. Yes. So now we need to make it more complex. So we will go from RL circuit to something more complex, which RLC network. And we will do the same. We have 3 steps which we need to follow. First, I need to label current in branches because my circuit here is only one loop. So we will have only one current. So the current will go from V, it will go to R, and from R it will go to L, and from L it will go to C, and then back to the source one more time. So in fact, we have here only one branch. So we will label the current. So we will have only I of t. We will have here I of t. So I of t will be my current. After that, we will look into elements or components which store energy or charge, right? So, and we will write the differential equation which describe it. So we will look into L and C, the inductor and the capacitor. For the inductor, we need to write the equation of VL. So in fact, from the table here, you can see that VL equal L di by dt. So this one will be one equation. Correct? VL equal L di by dt. And for the capacitor, if you look into the capacitor here, we have I equal, because we need to write first order differential equation. So we will get IC equal C dVC by dt, or I equal C dVC by dt. This one is VC. So we will write this equation as equation number 2. And according to the definition of a state space representation, which is x dot equal ax plus b, we need to get this x dot in one side. And it should be represented as a function of the states x and u input. And the output equation will be cx plus du. So we need to start with the state equation. We need to get this one in one side, di by dt, and the dvc by dt will be my states. So in this case, in fact, we will have 2 states. In this equation, we will have 2 states. So I need to write it in one side. So it will be like this one. Of course, IL equal I, so I will call it di by dt equal 1 divided by L multiplied by V, right? By VL, sorry, VL, right? And for the other equation, it will be dVC by dt. So we keep it dVC by dt. It will be 1 divided by C multiplied by IC. Just remove C, right? Remove C because it's I. IC is IR, it's the same current way. And we will remove this C. It will be just I. So we will look into the first equation. And we will look back into this x dot equal ax. X dot equal ax plus bu. It means that we need to represent the first derivative of my states as a function of the state. So if I have I and Vc will be my states. So we can say that, okay, x will be, in fact, it will be I and Vc. This one will be my states. So in fact, we need to write the first equation as a function of I and Vc and the input, which is V. We will look into VL. What is VL? Yes, VL, in fact, it's V minus VR minus VC, correct? So this one, we can say that this one will be 1 divided by L multiplied by, right? I will start with VR. It will be minus VR minus VC plus V, correct? So it will be 1 divided by L multiplied by, what is VR? In fact, it's I times R. So it will be minus R times I. So now we have C, we can see I. Minus VC, we will keep VC as it is because VC is one of my states, plus V. So it will be like this one. And of course, the second equation, it's as it is dVC by dt, it's I 1 divided by C multiplied by I. We will keep it as it is because I is a state. So in this case, we can go into, yes. So in more details here, we will get dIL by dt in one side, dVC by dt in the other side. So di by dt, it will be 1 divided by L multiplied by VL. VL is V minus I times R minus VC, right? Just to order it. And in this case, we will define my states. So I will have the first state will be I, x1 equal I, and x2 equal VC. If you want to just replace I and VC with the states, it will be like x1 dot, the first equation. This is the first equation. So it will be x1 dot equal 1 divided by L multiplied by V minus R times x1 minus VC, which is x2. Just order it. So x1 dot equal minus r divided by L multiplied by x1 minus 1 divided by L multiplied by x2 plus 1 divided by L multiplied by V. And we will go to the second equation. You remember that the second state x2 equal VC, so it will be x2 dot, just replace VC with x2. So this left-hand side, it will be x2 dot equal 1 divided by C multiplied by I, and the I is x1. So it will be like this one. So now we have two first order equations. This one, it's first order equation. This one is first order equation. We need to put it in matrix form. So when we need to put it in matrix form, we will have x dot capital equal a vector, and this vector consists of two values, x1 dot and x2 dot. We will write it in this form, x dot equal ax plus pu. So just to try to put it in matrix notation. So in the first, we will write the first equation in the first row. So x1 dot equal minus r divided by L multiplied by x1 minus 1 divided by L multiplied by x2, because it's row multiplied by column, plus 1 divided by L multiplied by V, which is the U, right, input. And for the second state equation, it will be x2 dot equal 1 divided by C multiplied by x1, and we will add here 0 and 0 because we don't have any other terms. So this one, we call it a state equation. And when you look into this state equation, you can see that we have two states, x1 dot and x2 dot, or x1 and x2. We have two states. Why we have two states? Because this RLC network has two storage elements. It has L and C. In the last example, we had only L, only one storage element, so we will have only one state. But this equation, or this RLC network, it has two storage elements, energy storage elements. So in this case, we will have two states. We will have x1 and x2. For the output equation, as I told you, the most important is the state equation. This is the most important because this is the one which will describe the dynamics of your system. For the output equation, it's something which we need to decide. Maybe someone of you will say, okay, I need to measure the voltage drop across the capacitor. I need to measure VC. So in this case, Y equal VC. What is VC? In fact, VC is one of my states. So I need to measure X2. So I will write it in matrix notation like this one. Y equal Cx plus du. So if I need to measure VC, so in this case, I need to measure X2. So C vector, it will be 0 and 1 multiplied by this one. So 0 times X1, it's 0, plus 1 times X2, it's X2. And of course, D equals 0 because we cannot see that VC is a function of the input, right? VC is a function of VC, but it's not function of the input. So the output equation will be this one. So this is state equation. This one will be my output equation. Maybe someone, he will say, no, I want to measure VL. I want to measure VL. So I want my output equation to be VL. So in this case, we will say that, okay, Y equal VL. What is VL? I need to represent VL as a function of my states. So we will look into the equation, Y equals Cx plus du, right? So it should be a function of my states. And my states are I and Vc. So we will look into VL, and we see that from Kirchhoff voltage law, V equal VR plus VL plus VC. We want to measure VC, so we will take VL in one side. So VL, it will be minus VR minus VC plus V. Remember, VC is a state. We will keep it as it is. This is X2. But what about VR? No, VR is not a state, but VR, in fact, it's I times R. So this one will be minus I times R minus VC plus V. So in this case, I can write this equation in this form. But just remember, I is, X1 is I. So I will write it like minus R multiplied by X1, correct? Minus VC. VC is X2. So minus X2 plus V, which is my input, U. I will write it in matrix form. So I cannot write here. So it will be like this one. I will do it here. So it will be a vector C, it will consist of minus R coefficient, minus 1, multiplied by x1 and x2, right? Plus 1 multiplied by U, in fact. So in fact, when we do this change, in fact, C vector, C in this case, this one will be C, this one will be D. So now we have different output equation. So the idea here, once you have a state equation, you can just focus on any parameter. If you want to control VC, you need to measure VC. If you want to control VL, you need to measure VL. If you need to control VR, it is a C. So maybe someone you will say, okay, I want to measure the voltage across R. This is my output. So in this case, Y will be VR, and we will try to represent VR as a function of states. Of course, VR is I times R, so it will be R times I. So in this case, in fact, it will be like it will be R times x1. So my output equation, it will be like this one, R 0 multiplied by x1 and x2. It will be like this one, right? So the output equation is something which we need to decide. The most important for us is to develop the state equation. Okay, so we have here another example, which is more complex example. It's example 3.1, and in this example, I need to check how much time we have now. Okay. Yes, it's 52 minutes, so we can finish this example and take a break and start part 2. So we will finish with this example. In this example, in fact, it's still RLC circuit, but it's more complex. RLC circuit, but it's more complex. It's still, we have only two energy storage element. We have here VL, correct? So we have that part. We have also that part, but we have two loops. So first, we need to label all of the branch current in this network. So for example, if you have branch current, so if you have the current coming from the source, we will go through L, we will call it IL. And after that, IL will be divided into part of the current will be called IR, which go through R. And in the second node, we will have IC. So the current will come here, and it will be divided into one part going R, we will call it IR. And the part will go to IC, and we will call it IC. So first, we need to label all branch current in the network. And after that, we will select the state variables. To select the state variables, we need to select the energy storage elements in my network. So in fact, we have here VL, because it will be L DIL by dt, right? It will be L DIL by dt. So this is the first storage element where we can write differential equations or something. And of course, IC, which is C dVC by dt, right? So we will go to this equation because it has di by dt, and then we will go to that part which has dVC by dt, right? So only those two from the table, because this is the only way to get x dot, because we need to get x dot because the state equation, it's a set of first order differential equation. So we will write VL, which will be L DIL by dt. We got, this is a first state equation. And the second equation, it will be IC equal C dVC by dt, this equation, right? We will get those two equations. As we did before, we will divide both sides by L by C, so we can get the IL by dt in one side, right? And the dVC by dt, so we can say that, okay, the first state, x1, it will be IL. And the second state, x2, will be VC. Those are my states. So dIL by dt, it will be x1 dot. And dVC by dt, it will be x2 dot, right? So we will get the IL by dt in one side. So it will be 1 divided by L multiplied by VL. We need to represent VL as a function of my states. You know, and the other equation also, it will be dVC by dt equal 1 divided by C multiplied by AC. Just we need to know that IL is one state, right? This one will be x1. And the VC, it will be one state. So this one will be x2. So now I need to represent the right-hand side in terms of my states. So now we have VL. What is VL? We have here VL. VL is not a state, so we need to represent it as a function of the states. In fact, VL, it's the voltage drop across here, it's VR, and it's at the same time also it's VC, correct? So the voltage drop here called VR, but it is at the same time also VC, correct? And the VC is a state. So we can just say that, okay, VL equal V minus VC. It's a Kirchhoff voltage law because V, the source, equal VL plus VC. I write it here V equal VL plus VC. So in this case, what will be the value of VL? VL will be V minus VC. So we will substitute V here with V minus VC. So it will be 1 divided by L multiplied by V minus VC. V is the input. We will call it U. And the VC, in fact, it's a state, which is X2. So now we are happy with that part. We'll go to the second equation. And in the second equation, it's dVC by dt equal 1 divided by C multiplied by IC. What is IC, in fact? What is IC? IC, in fact, it's, I need to represent IC as a function of the states, correct? So what is IC? In fact, IC, it's IL minus IR, right? IC, the current here, equal IL minus IR. And IL is a state, so this is very good. So we will substitute IC by IL minus IR. And IL is a state, is X1. So this is okay. Still IR, what is IR? In fact, it's VC divided by R, right? It's VC, IR is VC divided by R, and VC is a state. So in this case, we can just replace IC with IL minus 1 divided by R multiplied by VC. Remember, VC is X2, and IL is X1. So now we can represent IC using the states. So just to substitute this value in the above equation, so dVC by dt, it will be 1 divided by C multiplied by IL minus 1 divided by R multiplied by VC. So now we have this equation, we will call it equation 1. And we have this equation, we will call it equation 2, just to try to arrange it, order it, right? And try to write it as a function of the states. So we know that the first state will be IL, so IL equal X1 and VC equal X2. So just write those two equations one more time. So we will look into equation 1, which is the IL by dt. So we will call it X1 dot. So this one will be X1 dot equal, just order it. So it will be minus 1 divided by L multiplied by VC, which is X2, plus 1 divided by L multiplied by U, which is V. So this is my state equation. I will call it 1 dash. We will go to the second equation, which is a part. It's the same. VC is X2. So dVC by dt will be replaced by X2 dot equal. Yes, IL is X1 and VC is X2. So just to write it in a nice way. So it will be 1 divided by C multiplied by X1 minus 1 divided by RC multiplied by X2. So this is equation number 2. So try to write equation 1 dash and 2 dash in matrix notation. So we will define a state vector X dot equal X1 dot and X2 dot equal matrix A multiplied by X, right? X equal X1 and X2. So we will write the first equation in the first row. So X1 dot equal 0x1, because we don't have here any x1 in this equation. So it will be 0 multiplied by x1 minus 1 divided by L multiplied by x2. So this is the first state, the second state, plus 1 divided by L multiplied by U. So 1 divided by L multiplied by U. We will go to the second equation. X2 dot equal 1 divided by C multiplied by x1. So this one will be 1 divided by C multiplied by x1 minus 1 divided by RC multiplied by x2 plus 0. So this one will be my state equation. This state equation, it's fixed for any system. So this state equation, it's like a trademark for any system. It's a fingerprint of your system. We cannot change it. So if you are working in a system in Norway, in China, in India, you must get the same state equation, because this is the fingerprint of your system. This is the system dynamics. A, we call it system matrix, and B, we call it input matrix, or vector. So now we need to get the output equation. So the output equation, as I told you, the output equation is something that will be different from system to system, or from a person to a person, or a company to a company. So for example, in this example here, we need to control IR. We need to control the current cross resistance IR. So Y equal IR. What is IR? IR, in fact, it's VC divided by R. So it will be VC divided by R. And remember, VC is X2. So it will be 1 divided by R multiplied by X2. Write it in matrix notation. So it will be this vector multiplied by this vector. Coefficient of X1 is 0. Coefficient of X2 is 1 divided by R. So we can say that, okay, Y equal CX. So this one will be the output equation. For the output equation, you can have many other different output equations, right? So maybe someone will say, okay, now, no, I want to control the voltage drop across VC. So my output will be VC. But VC is a state, in fact. VC is a state which is X2. So in this case, output equation will be like 0, 1, multiplied by X1 and X2. So it could be something like this one. Maybe someone he will say, okay, no, I want to control VL. So Y will be VL. But what is VL? VL, in fact, it's a source minus VC. So it will be minus VC plus V. What is VC? In fact, VC is X2. So it will be minus X2 plus U. So in matrix notation, it will be 0 minus 1 multiplied by X1 plus X2 plus U. So it will be like this one. So the output equation, it's different. It's different. So anyone can select a different output equation. But the most important here is to get the state equation correctly, because the state equation is fixed. It is a fingerprint of your system. So now we will finish here. So the video will not be too long, and we will meet again in part 2 of chapter 3, where we will solve example 3.3. Thank you.